Welcome to topic 7.6 and 7.7. Our video today is going to be on finding general solutions and particular solutions using initial conditions and separation of variables. We've been talking a lot about differential equations in this unit. Today we're going to talk about how to solve a differential equation for a given variable. All right, and the first step in every one of these problems is going to be something called separation of variables. Up until now, we have only been able to solve two types of differential equations analytically. Given that the first derivative is some function, or the first derivative is some function, and the second derivative is some function. That's it for now. In this section, we're going to solve a more general type of differential equation. The strategy we're going to use is rewriting the equation so that each variable occurs on only one side of the equation. This strategy is called separation of variables. So here you can see a couple examples of separation of variables. Here are some examples of differential equations with variables not separated. On this side, you can see there's both x and y's on the left. Same thing here, both x and y's on the left. Same thing here, both x and y's on the left. By doing some algebra and rearranging, you can see over here, only y is on one side, only x is on the other. Y is on one, x on the other. Y is on one, x on the other. After we do that first step of separating the variables, then we can use our integration techniques to integrate both sides, and then our algebra techniques to solve for y, if possible. Sometimes solving for y is really difficult to do. So in those cases, we don't need to actually solve for y. Let's start off with a pretty basic differential equation problem. Y prime equals 2x over y. The first thing I would suggest you doing in problems like this is to rewrite y prime as dy dx. And you'll see y in the next step. So the next step, what we want to do is we want to get all the y's to one side, all the x's on the other. It's usually a lot easier, since dy is already in the numerator here, to get all the y's to that side, and since dx is in the denominator, to move all the x's to the other side. Okay? So to do this, what we're going to do is multiply both sides by dx. Now we're going to do this in two steps, but really you should be able to do this in one step. We get dy equals 2x over y dx. And then we're going to multiply both sides by y. And that gives us y dy equals 2x dx. And you can absolutely do that in one step. Now we're going to take the antiderivative of both sides. So antiderivative y dy and the antiderivative of 2x dx. That would be y squared over 2 equals 2x squared over 2, or just x squared, plus c. Now you might be wondering, why didn't I put plus c on both sides? Let's pretend for a second you did. Plus c, right? This is just some constant. This is just some constant. Now if we subtract this constant over here, we have a constant minus a constant. Guess what we get? Another constant. So you don't need to write the plus c on both sides. You only need to write the plus c on one side, and typically we just write that on the x side, or the independent variable side. Now your job is to solve for y, if possible. This is a pretty easy one to solve for y, so let's do that by multiplying both sides by 2. So same as before, you don't have to write plus 2c, because 2 times c is just another constant, so we could just write plus c. Most people in the calculus world just write plus c. If you wrote plus 2c, it's fine, but it's completely unnecessary, because 2 is a constant, c is a constant. When you multiply them, you just get another constant. Finally, solving for y, we get y equals plus or minus square root of 2x squared plus c. Example 2, solve the differential equation. I'm going to copy it down here first. dy dx equals, but while I'm copying down, I'm going to factor out the y. So once again, I would encourage you to get all the y's to the left, all the x's to the right. I'm going to do that in one step this time by dividing both sides by y and multiplying both sides by x dx, sorry, at the same time. So I multiplied this to both sides and divided this to both sides. And I'm left with this. All right, now taking the antiderivative of both sides. The antiderivative of 1 over y, remember, is ln absolute value of y. And over on the right side, we have 3x plus x squared over 2 plus c. This is a logarithmic equation. Right? To solve this for y, what we're going to do is we're going to take the logarithmic equation and change it into an exponential equation. Technically, this is log base e, so it's going to be e to this power equals y. In other words, y equals e to the 3x plus x squared over 2 plus c. Technically, that is a perfectly acceptable answer, but what we could do is we could rewrite it like this: e to the 3x times e to the x squared over 2 times e to the c. Why do I want to do that? Because e to the c, e is a constant and c is a constant. So e to the c can be written as just some other constant c. So now I get e to the 3x times e to the x squared over 2 times some constant c. And rewriting this a little bit better, we put the c in front, so it would be c e to the, and I could put these two exponents back together, 3x plus x squared over 2. And that would most likely be the answer if this is a multiple choice question. Maybe even having you do a common denominator up here as well, which would give us 6x plus x squared all over 2. So they're called general solutions. Why are they called general solutions? Because there's infinitely many solutions that look like this. Infinitely many solutions that look like this. Now we're going to be asked to find particular solutions. So of all the solutions that are possible, the one that goes through a specific point. What we're going to do is the same first step. Get all x's on one side, get all y's on the other. So rearranging this, if I divide both sides by y, divide both sides by x squared over 4, and multiply both sides by dx, I get that. So that's our separation of variables. Now if I take the antiderivative of both sides, on the right side, we're going to do some substitution. Let u equal x squared plus 4, so du equals 2x dx, or 1/2 du equals x dx. So now my equation looks like this: 1 over y dy equals 1/2 1 over u du. Taking the integrals, now we get natural log absolute value of y equals 1/2 natural log absolute value of u plus c. Now if I resubstitute back in, I get here. All right, so now let's use our initial condition. Our initial condition, y is 2 when x is 3. So I'm going to put that in. Y is 2 when x is 3. 3 squared plus 4 is 13. Multiply both sides by 2. Actually, let's not even do that yet. Let's just subtract, though, the 1/2 ln 13 to the other side. Might be easier to do it that way. So my c is ln 2 minus 1/2 ln 13, which we can write that a little bit differently if you want to. You can write that as ln 2 minus ln root 13, which is ln 2 over root 13. Clean that up a little bit. So c equals ln 2 over root 13. All right, now let's go back to here. I'm going to rewrite my equation again as ln absolute value of y equals 1/2 ln absolute value of x squared plus 4. I'm running out of room here. Let's go down here. I got some more room to work with. Plus c. So plus ln 2 over root 13. So now if we take e to the power like we did in the last one, we rewrite this as an exponential equation. So that would be y equals e to this whole thing all right, and after doing some algebraic manipulation, we have e to an ln power. Remember, we could split this up into this times e to this power. And e to the ln, so it's going to be root x squared plus 4 times 2 over root 13. Because e to the ln will cancel each other out, and all we're left with is what's inside the natural log. And that would be our final answer. Now, I did also take this 1/2 and make this a square root on here as well. You don't have to do that, but it does make it look a lot cleaner if you do. Example 4 is another initial condition problem, which means we're going to be finding a particular solution. So first of all, this looks like a pretty crazy looking problem here. To get all the x's and y's separated from each other, we have to do a little bit of work. All right, the first thing we're going to do is subtract this to the other side. So we get e to the negative x squared times y squared minus 1 dy equals negative xy dx. Now, if I divide both sides by y and divide both sides by e to the negative x squared, I get this. Y squared minus 1 over y dy equals negative x over e to the negative x squared dx. Now we're going to take the antiderivative of both sides. But before we do the antiderivative of both sides, we got to do some work on both sides. On the left side, we can rewrite that as y squared over y, which is y minus 1 over y dy, which I can actually rewrite as, no, let's leave it like that. That's probably the best way to write it. And on the right side, I want to do some more substitution. So let u equal negative x squared. So du equals negative 2x dx, or 1/2 du equals negative x dx. We have a negative x dx right here. So we just have 1/2 1 over 1 over e to the u du. I can rewrite that right side as e to the negative u du. All right, now taking the antiderivative of both sides, I get y squared minus ln absolute value of y equals negative 1/2 e to the negative u plus c. Back substituting, put that negative x squared back in there. So this becomes e to the x squared plus c. Let's take a look at our initial condition. 0, 1. So we have 1 minus ln 1, which is 0, equals negative 1/2 e to the 0, which is just 1, plus c. So I have 1 equals negative 1/2 plus c. Actually, wait a second. I just caught a little problem I made here. This is supposed to be y squared over 2. Y squared over 2. I took my antiderivative wrong. The antiderivative of y is not just y squared, it's y squared over 2. This would be 1/2 equals negative 1/2 plus c. Add 1/2 to both sides and we get 1 equals c. All right, so put that back into this equation right here. And we're not going to get anything too pretty here, that's for sure. So we have y squared over 2 minus ln absolute value y equals negative e to the x squared over 2 plus 1. And that's really as far as you can go. If you wanted to, you can multiply through by 2 to get rid of the fractions. And that would probably be what we asked of you if it was multiple choice. But not going to be able to solve that for y, at least not without some type of calculator, in my opinion, would we be able to solve that for y. So we are okay leaving that as your final answer. Hopefully you caught my integration mistake back here and were yelling at the screen to fix my mistake. All right, last one, example 5. Find the equation of the curve that passes through the point 1, 3 and has a slope of y over x squared at any point x, y. Be sure to state the domain of your solution equation. Okay, this is our differential equation right here. Really, that's saying dy dx equals y over x squared. All right, so do some separation of variables. We get 1 over y dy equals 1 over x squared dx. So antiderivative of 1 over y dy equals antiderivative. I'm going to write this as x to the negative 2 dx. So that's ln absolute value of y equals x to the negative 1 over negative 1 or negative 1 over x plus c. Our initial condition was 1, 3. So ln 3 equals negative 1 plus c, or ln 3 plus 1 equals c. Put that back into, oh, not there, this one. So we get ln absolute value of y equals negative 1 over x plus 1 plus ln 3. Rewrite that as an exponential equation. So y equals e to the negative 1 over x plus 1 plus ln 3. All right, we talked about this earlier, but what we could do is we could think of this as e to the negative 1 over x times e to the 1 times e to the ln 3. And this is all just 3. So I can write this as y equals 3 e to the, and now I can combine these back together, and I can go 1 minus 1 over x. And that's going to be the most simplified version of our answer. Unless, of course, you want to get a common denominator up here, so it would be x minus 1 over x. But that would only be if it's a multiple choice problem. And that will do it for topic 7677. Thank you very much. We have one more topic to talk about in this unit, and hopefully we'll see you again next time.